How long do you have?
Like 15-minute class. He said 7, but it's 15. The class was 10 minutes. And so in 15 minutes, it was 7 questions, and most of them had 4 parts to them. So it was like you could not write fast enough.
It wasn't hard. Jay, there's a difference between hard and achievable.
Hard. Come on.
It wasn't hard, but there was like 20 questions.
No, there wasn't.
4 parts for all the questions.
It really was only the last part. You just needed those to get to that.
So here's the calculation. Now explain.
They were allowed to use Wolfram model.
That makes it a lot easier. That does make the exam easier. You're all reasonably entitled to moan at him all you want. Once you see the answers, you might hit yourself. So let's wait and see. All right, here is a graph. Consider this as if it was a set of roads connecting villages. If any road closes, what happens to my graph? If you close any single road, or Reese, if we delete any one edge, okay, it becomes disconnected. So let's think about this in general. If I had a subgraph, I could take away edges. If I take away an edge, I don't change the vertices at all. If I have a collection of edges, then I can think of G take away X, where X is a subset of edges, as doing the same idea. But leaving all the vertices behind. So the vertices stay the same. If removing any edge disconnects the graph, that edge is a bridge. And those, once we remove a bridge, I have 2 distinct components. One of those components will contain you, the other component will contain thee. Why is that true? Why do I know that there's more than they're not just adjacent to each other? Because I'm telling you that we now have components, right? So it's more than they're not just adjacent to each other. There can't be any path other than the edge from U to V that connects them. Because if there were, then removing that edge, there'd still be a way to get from one to the other. It would still be connected. By the way, if I start with a disconnected graph, then I can talk about bridges in each component. You have a bridge in one component, a bridge in another component. But a bridge is something that increases the number of components when you take it away. So if I remove that edge and I separate U and V, then I've increased the number of components by 1. What if V or U has degree 1? When I remove that edge, that component only contains that one vertex. What did we call vertices of degree 1? Vertex of degree 1. A leaf, the end of a branch, or an end vertex. So if I have a leaf or an end vertex, I pull away that branch, I've isolated that node. This particular graph already has 3 components, has 4 bridges. Kind of hard to see here, but they're all in bold. I've got an end vertex. I must have a bridge. I've got an end vertex. I must have a bridge. End vertex must have a bridge. And my other bridges are right here. In that first graph I showed you, all of my edges are bridges, because removing any one of them is connecting the graph. An edge is a bridge if and only if it is never part of a cycle. Sure. Why? I've written it as a theorem. It should be provable. If my vertex is, if my edge is part of a cycle, then its degree has to be at least 2. Okay. That vertex has degree 3, but there's still a bridge on it. A bridge incident to it. I'm not sure that's enough.
The cycle you can get from any, you can start at any vertex and get back to it. You can take away that and you can still get all around the cycle.
I can go the other way around the cycle, right? So if an edge is part of a cycle, then that edge can't be part of a bridge. That edge can't be a bridge. That's one of the 2 proofs. What's the other one? Well, it's the exact same argument. If this is a bridge, then when I remove it, I disconnect it. So there can't be any other way to get from U to V. Otherwise, the graph would still be connected. Both proofs you just said, we didn't write them out, they're both proofs by contraposition. Both proofs by reversing what our argument is. If I can get from A to B 2 different ways, then that's not a bridge. This actually leads me back to a better definition of that first graph. That graph had no cycles at all, right? What can you tell me about my graph if it contains no cycles at all? Every edge is going to be a bridge. A tree is an acyclic connected graph. We kept writing G for graphs, right? I'm going to write T for trees. So if I write tree, we're going to make an assumption it's a tree. Why connected? Well, I want to use connected because if I have more pieces and they're all acyclic, then I can think of that as a bunch of trees, and then that's a forest. So I know it's lame, but each forest is made up of trees. Let's think about trees of a particular order. How many trees could I make of order 6? Wait, let me use the right word, Mia. How many non-isomorphic trees can I make? Well, let's think about what could happen. If I want to build a tree, order 6, what's the maximum degree I could have? So let's suppose I made a vertex of degree 5. Can I put any more edges anywhere on this graph? Why not, Reese?
You would connect like any of the other to each other, you have a circle.
As soon as I were to make another edge, I'd have a triangle, wouldn't I? Okay. So what if my highest degree, instead of being 5, is 4? I need another vertex, right? I'm missing one. So here's one. There's another vertex here. If it's a tree, it needs to be connected. What do I do? And no matter which one I do, it's effectively equivalent, right? All you do is just turn the picture. No matter which of the 4 you connect it to, those are all isomorphic. So here, there's your maximum degree of 4. What if my maximum degree is 3? Attach 2 in a row. Talk to me about what you mean by 2 in a row. So like this, connected to this or connected to this? Here? Okay, what else could I do? Instead of adding the other one up here, I could add it down here, right? What else could I do? So put it up here instead of down here? Isn't that the same picture just turned? So that's isomorphic. So that's the problem with this. I'm glad you saw that, but yes, that's unfortunately equivalent to this one.
Instead of like variations, you just do it.
It's going to be isomorphic. I could attach both of them to the same vertex rather than two different vertices. And that turns out to be it. Now, I will freely admit that I don't normally draw these three this way. I draw them a little differently, and I'll show you those pictures in a minute. But I have maximum degree 5, maximum degree 4, maximum degree 3, maximum degree 2. Shook your head, Reese. Why? If everything was degree 2, it would be a cycle. But I said the highest degree was degree 2. I could make a path. Then the ones on the end have degree 1, but they're still highest degree is degree 2. If my highest degree is degree 1, I'm in trouble, aren't I? Because then it's not connected anymore. That's it, by the way. These are all the possible trees of order 6 that are not isomorphic to one another. What do they all have in common? Maybe we'll think about that. You don't have to have an answer right away. Yes, but I told you that at the beginning. I told you they were all of order 6. They all have the same number of edges. They all have 5 edges. Now, normally, I draw this one looking more like one of these. Page 88, here are those 6 trees. Maximum degree 5 is a star. This is the maximum of degree 4. I drew these bottom 5 as a cross, but they drew it as a Y here. This looks like 2 stars, a star of 3 and a star of 3 that are connected. A short Y and a long Y. This is this graph. A short Y with a long tail. This is this graph. A 1 and then 2 of 2. A 1 and 2 of 2. Those are my 6. If you start here and you take away all of the end vertices, what do you get? Remove the vertices, you remove the edges that go with them. Cut that off, cut that off, cut that off, you get a path, right? If you remove the end vertices from here, you get a path. The ones that only have degree 1. But if I remove the end vertices from here, I remove more things, I still get a path, don't I? Path of length 1, but it's path. Right? If I have any tree of order 3 or more, and removing end vertices results in a path, then I could redraw it. So all of the end vertices pointed in the same way. Here's a tree. The 2 edges that are pointed upwards at the moment, I'm going to move them so they're pointed down. I just tilted stuff. If you remove all the end vertices, you get a path of length 3, don't you? But doesn't it look like it's crawling along? I wish I was making this up. Any tree where you remove the end vertices and the result is a path is called a caterpillar, because it looks like it's crawling along. Well, because if I had a path with 3 vertices and I removed it, I'd be left with 1 vertex. That's not a path. So I need at least... No, it says right here, a path of order 3 or more. The single vertex is a path of length 0. I don't like it, but it's lame. It makes the definition. I can tell you outside of this textbook, I have never, ever heard the term caterpillar used in graph theory anywhere else. But it's in here, so I wanted you to hear it. The path that's left after you remove the end vertices is called the spine, which sounds like a computer science term. You have a network backbone. Network connectivity is a graph theory problem. You'll notice that in all of these trees that we drew, I did not particularly choose any vertex and make it special, denote it somehow. Ooh, look at this one. But you could pick a particular vertex and say, this is the starting point of my tree. In which case, if we designate that vertex, that's where my tree starts. What are we going to call the place where a tree starts? A root. And then we have a rooted tree. The same tree can be rooted in many different ways. I could take that double star there, the one on the left, and I could pick any of those to be the root. But if I picked any of the outside 4 to be the root, all 4 of those would be isomorphic, wouldn't they? If I picked either of the inside 2 to be the root, those would be isomorphic. So there are fewer rooted trees that are not isomorphic than there are trees that are not isomorphic of a particular shape. Almost always, we put the root of the tree at the top and work down by distance away. Go back to the very first graph I had drawn today. If I make V2 the root, V1 and V3 are distance 1 from there. V4 and V5 are distance 2. V6 and V7 are distance 3, and they're in layers moving down from the root by distance. Some graph theoreticians will draw a root on the left and extend their branches for their tree to the right. It is very rare that you will see a rooted tree with the root drawn at the bottom. Why? I don't know how far down the damn page to go to grow the tree, do I? But if I start with the root at the top, I can just keep going. I don't make these rules up. Somebody in the typesetting universe made these up. If you're in a tree and you pick any two vertices, why can there be one and only one path? If there were two different paths, I go first from U to V and then I go back from V to U along the other one, that's a cycle. It's not a tree, it's got a cycle. If it's a tree, it has no cycles, therefore every edge is a bridge. If I go from U to V and I take one of those away, then I've disconnected U and V. Oh, can't be a second path. Which means trees must have leaves. Why does a tree have to have a leaf? Well, other than the trivial one, that's just one vertex, where it's the root and the leaf at the same time. Now, I can actually write out a formal proof for this, just like I could write out a formal proof for the previous one. But I didn't. I talked through the idea rather than write the formal proof. The formal proof's in the textbook, people. If I'm going to want you to go through it from scratch, then I don't want to give it to you somewhere else. Go read it if you want the formal proof. Why must every tree have at least two leaves?
Because a path has start and an end to inverts.
Yes, kind of.
So that there's a guarantee that there's no cycle between them.
Because if there's not an end, then I'm going to come back around somewhen, right? Suppose I had two vertices in the longest possible path from U to V, right? There's a smallest path, that's the distance, right? But we could look at the longest possible path. Well, that means one of two things. Either U and V are adjacent to each other directly, or there's some vertex not on this path. If there was a vertex that's adjacent to either U or V, that's not on this path, I could make a longer path. Oops. So it's got to be at least one vertex that isn't. But that means that that vertex is also not adjacent to all of these in more than one way. Otherwise, I'd have a cycle. That means that this vertex over here must have degree 1. It can't be adjacent to anything else. This vertex over here must have degree 1. It can't be adjacent to anything else, because if it was, I could get a longer path. And we just said we were starting with the longest possible path. You're absolutely right. It's got ends. But I can't just look at any path and have ends. I got to look at the longest possible path to find ends. And if I had something longer, I'd end up with a cycle. Can't do that. It's a tree, no cycles. But that automatically leads me to my favorite thing, and that's that all those trees of order 6 had 5 edges. I claim that any tree of order n can never have more than n minus 1 edges and must have exactly n minus 1 edges. Advanced warning. The proof of this is an induction argument. The proof by induction. If you have a tree of order one vertex, how many edges do you have? That was easy. There's my base case, check. So let's suppose I have some tree of order k and size k minus 1. You know you've got 2 n vertices, right? Let's pick one of them. Take that one away. I've taken away 1 vertex and 1 edge. I've gone down from k and k minus 1 to k minus 1 and k minus 2. So if I start with a tree of size k, and I go to one of the n vertices, and I add on 1 vertex, don't I increase by 1 edge? There's your reduction argument. Add 1 vertex, you add 1 edge. But only if you add it to an n vertex. Or if you add it without building a cycle. And I want to keep a tree, so I have to be able to add it without building a cycle. Ta-da! If I go from k to k plus 1, I've made it. But now you can do all the size arguments that we did for regular graphs with trees, because you know every tree has a fixed size. By the way, if this is true for a tree, what can you tell me about a forest? There's another half a sentence to be written here. What's a forest?
Size n minus k.
Where k is
The amount of trees.
the number of trees involved. Because I lose 1 for each tree. Switch back to regular graphs from trees. What do you now know about any connected graph? And don't we also know the maximum number of edges as well? The maximum possible number of edges you can have. I think you're thinking about degrees, the handshake result, which had 2m in it. But that's I want to know what m is.
Oh, is it 2n?
2 to the n. 2 to the n.
Would be
2 to the n would mean for each vertex I could put 1 in or take 1 out, but then somehow I'd have, if I put them all in, I'd have, for 4, I'd have 16 edges. Can you use 16 edges on 4? In a pseudograph, multigraph, kind of, maybe, but I'm not sure. But in a simple graph, at most, every pair of vertices gets an edge, right? That's our complete graph. Kn would have all the possible edges you could put in. So here's my question. Province stats people, how many pairs of vertices are there? N choose 2, and we have a formula for that. What's n choose 2? You know both the minimum and the maximum possible size of a graph. Damn, it pays to learn how to count, doesn't it? And some days it's like, I know there's a formula for this. I just don't know what it is. Okay. What was my definition of a tree again? So no cycles, connected. But we just said the minimum possible size of any connected graph is n minus 1. And if you're a tree, you have to have that size. That turns out to be an if and only if statement, provided one of the other two is true. If you tell me that my graph is connected and acyclic, by definition, if it's a tree. If it's connected, and number 3, there are the right number of vertices, can it contain a cycle? If it contains a cycle, then it won't be connected, because we will have used an edge that we could have used to get to this vertex n to make a cycle instead. So we'll break connected by trying to make a cycle. If it's connected, if it's acyclic and it's the right size, then it's a forest. It might not be connected. But since it has this many edges, then we are connected to each vertex because we don't have any cycles. I only need 2 of 3. Knowing how many edges, knowing that I'm connected, knowing that I don't have cycles. I need 2 of them guarantees me a tree. Trees are in every other graph. So let's suppose I have a tree with k vertices. Consider for a moment the complete graph on k vertices. That's the extreme other end on k vertices, right? You could take away all sorts of other edges and be left with the tree that you started with, right? T is isomorphic to some subgraph. But in the complete graph of order k, every vertex has the same degree. Every vertex has degree k minus 1. And since they're all the same, that's the lower and upper degree limit. Well, it turns out that that is also true for any graph whose minimum degree k minus 1. So every graph on the right number of vertices appears in some larger graph whose minimum degree minus 1. Why do I need the minimum degree to be k minus 1? I didn't just pull that out of my ass. There better be a reason for it.
T has to have a graph of that size, then it's really proper.
T has to have that many edges, right? But it doesn't say anything about the degrees, right? As a matter of fact, in my graph, in my tree, every vertex is either degree 1 or 2 or 3 up to k minus 1. But it's the fact that the tree could look like a star. And that vertex has degree k minus 1. So if I didn't say anything about what kind of tree this was, it might have that one k minus 1 in there. And that's why the minimum degree needs to be k minus 1. Again, proving this is an induction argument. I think it's worthwhile for you to read these theorems. But if this is part of chapter 4, it is not part of the exam, you can probably put it off a little while. I did realize that I was supposed to do bridges on Wednesday, and I put them off until today because I spent time going over equivalence relations instead. I thought that was useful. So I jammed these together. I did reprint the schedule, and I looked carefully, and there is still 2 days before stuff is due. So I didn't screw you guys over on due dates. But 4.1 and 4.2 are due on separate dates. We'll see you all on Monday. Have a lovely weekend.